Hello, welcome to chemistry session. Today's session, I'm going to deal about xenon oxytetrafluoride, xenon oxy dioxydifluoride, xenon oxy difluoride. So the oxy halides of the xenon, oxy fluorides of xenon are discussed in this session. Um, previous class, I've told you about the noble gas chemistry class, chemistry of the noble gases. And today's class, it is about the xenon oxyfluorides. The oxy halides of the xenon are generally oxyfluorides of xenon. So the xenon forms three oxyfluorides. One is xenon oxy tetrafluoride, xenon dioxydifluoride, xenon oxydifluoride. Now, xenon oxy tetrafluoride. What is its preparation? Xenon oxytetrafluoride, it is xenon oxytetrafluoride is a colorless, mobile, oily liquid. Its freezing point is minus 46 degrees centigrade. So just imagine it's a colorless, mobile, oily liquid. And at minus 46 degrees centigrade, it gets freezed up. And let us have a look onto its preparations. Xenon oxytetrafluoride, it is prepared by partial hydrolysis of xenon hexafluoride. Xenon hexafluoride here on partial hydrolysis. Here it reacts with this water and xenon oxygen is incorporated and two fluorines are eliminated outside. So xenon oxytetrafluoride is formed with elimination of two hydrogens and they form 2HF. Xenon oxytetrafluoride and hydrofluoric acid. Now the second preparation is by the action of xenon hexafluoride on silicon dioxide. So xenon hexafluoride, when reacts with silicon, the silicon dioxide, it forms xenon oxytetrafluoride and silicon tetrafluoride is liberated outside as a byproduct. This xenon, oxygen and 4 fluorines react. Just see the balance. Well, again, the remaining fluorines form the silicon tetrafluoride. So as this yellow color liquid, as soon as the yellow color hexafluoride, hexafluoride is yellow in color. This yellow color will disappear and you get a colorless liquid, that is xenon oxytetrafluoride. The contents they're immediately quenched with the solid carbon dioxide so that this explosive xenon trioxide can be avoided. This, as we have told you previously, xenon trioxide, it's an explosive one. So in order to avoid that one, immediately you have to quench it with the solid carbon dioxide. Next, coming to the properties. You can still have some more preparations. I've discussed you only two preparations for oxytetrafluoride. That is hexafluoride hydrolysis and oxytetrafluoride on hydrolysis. Again, it may give trioxide. And xenon hexafluoride and reaction with the silicon dioxide will also give xenon oxytetrafluoride. Xenon trioxide on reaction with xenon hexafluoride, it gives xenon oxytetrafluoride. Xenon trioxide on reaction with xenon hexafluoride gives xenon oxytetrafluoride. So you can prepare this xenon oxytetrafluoride using water, silica, and xenon hexafluoride. Right? Now, let us have a look onto the chemical properties. As I've told you, it is a colorless compound and its melting point is it is about minus 46 degrees centigrade. It is reduced by hydrogen to xenon. You can see the reduction generally is nothing but reaction with the hydrogen is reduction. Xenon oxytetrafluoride on reduction or reaction with hydrogen gives xenon. This oxygen and H2 will form H2O, and this fluorine and hydrogen will form HF, the byproducts. Now, it reacts with water or silica to form another oxyfluoride. Xenon dioxy difluoride, in which xenon remains in the same oxidation state. Further reaction gives a explosive trioxide. It gives explosive trioxide. Now we'll see action with water. Xenon oxytetrafluoride on hydrolysis H2O, it gives dioxydifluoride and it gives 2HF. Next, xenon dioxydifluoride on reaction with water gives xenon trioxide and HF. Similarly, xenon oxytetrafluoride on action with silicon SiO2, it gives xenon dioxydifluoride and silicon tetrafluoride is liberated as the byproduct. Similarly, xenon dioxydifluoride on reaction with silica, it gives xenon trioxide and silicon tetrafluoride. So this is the action of water and action of silica. Now let us see the second oxyfluoride, that is xenon dioxydifluoride. Let us have the preparation. Preparation for this xenon dioxydifluoride. Even this is a crystalline solid, xenon dioxydifluoride. It is a colorless crystalline solid. It melts at 30 degrees centigrade, easily hydrolyzed to give xenon trioxide. Xenon dioxydifluoride, this colorless crystalline solid, how it is prepared, we'll see. It is prepared by mixing xenon trioxide and xenon oxytetrafluoride at room temperature for about minus 80 degrees or nearly minus 78 degrees, nearly 80 degrees, minus 80 degrees. Trioxide and oxytetrafluoride gives xenon dioxydifluoride. And now this can be purified by fractional distillation. And it is formed when xenon oxytetrafluoride is hydrolyzed or reacted with silica. It can also be formed when xenon oxytetrafluoride is hydrolyzed or reacted with silica. Xenon oxytetrafluoride on reaction with silica, you can see 2XeO2F2 and silicon tetrafluoride is formed. And xenon oxytetrafluoride on hydrolysis, it gives xenon dioxydifluoride and 2HF is formed. And this on reaction with silica, it gives dioxydifluoride, and similarly on hydrolysis, it forms dioxydifluoride. As I've told you here, dioxydifluoride, how it's formed. On hydrolysis, it's formed. The same reaction is here. Xenon oxytetrafluoride on hydrolysis gives xenon dioxydifluoride. Now we'll have a look onto the properties. It is colorless solid. It is the colorless solid. It melts at minus 30 degree, 30 degrees centigrade or 30 to 31 degrees centigrade. It can be easily hydrolyzed to give xenon trioxide. Xenon dioxide difluoride on hydrolysis gives xenon trioxide and 2HF is formed. Xenon dioxide difluoride on hydrolysis gives xenon trioxide and HF. Next. Now let us go for the remaining compounds of the xenon. Xenon trioxide. Xenon trioxide, the oxides of the xenon. Previously, I told you about the xenon oxyfluorides. Now we'll see only the oxides. Xenon trioxide. Xenon trioxide, it is prepared by hydrolysis of xenon hexafluoride or xenon tetrafluoride. Here, xenon tetrafluoride on hydrolysis gives xenon oxide. And xenon is formed, here HF and oxygen is formed. Xenon hexafluoride on hydrolysis gives xenon trioxide and HF. It acts as a powerful oxidizing agent in the acidic medium. For instance, it oxidizes plutonium, this plutonium plus 3 to plus 4 oxidation in presence of H plus ions. You can see the reaction. 6 plutonium ions on xenon trioxide. 6 H plus ions gives 6 plutonium, xenon and water. So this is the way the xenon trioxide it is prepared, and the property. From tetrafluoride we are able to prepare by hydrolysis, and from hexafluoride also we are able to prepare xenon trioxides. Now let us have a look onto the structure of the xenon compounds. Coming to the xenon compounds, difluoride, xenon difluoride, XeF2, it is plus 2 and linear shape. Tetrafluoride, XeF4, it is plus 4 oxidation state and square planar. Xenon hexafluoride, it is having plus 6 oxidation state, distotal, octahedron, and pentagonal bipyramidal shape. Xenon trioxide, it is the xenon is in the plus 6 oxidation state with pyramidal structure. Yeah, later on I'm going to give you the hybridizations and the geometry. Xenon dioxide difluoride, where the xenon is in the plus 6 oxidation state, and trigonal bipyramidal. Xenon, it is getting the trigonal bipyramidal shape. Here, the trigonal bipyramidal, we'll see. For xenon difluoride, the linear shape. How you're getting the linear shape? What is the hybridization behind this one? So, oxygen difluoride, the xenon difluoride, it is getting the sp3d hybridization. Xenon difluoride is getting the sp3d hybridization, and the shape is linear. Bond distance you may have around 2 angstrom. The oxidation state here for the xenon, it is plus 2 oxidation state. You get 2 bond pairs, and it is in axial manner, the bond pairs. The lone pairs are 3 lone pairs. So 2 bond pairs and 3 lone pairs. And the position of the lone pairs is equatorial. So position of the lone pairs is equatorial. Position of the bond pairs is axial. Now we'll see xenon tetrafluoride. In xenon tetrafluoride, you will get the square planar structure for xenon tetrafluoride. sp3d2 is the hybridization. Square planar sp3d2 hybridization, square planar structure. Xenon, it is in plus 4 oxidation state, and the bond pairs are 4 equatorially arranged. lone pairs are 2 axially arranged. Next, coming to the hexafluoride. Hexafluoride, the structure is in xenon hexafluoride. It is sp3d3 hybridization. Xenon is in +6 oxidation state. We get distorted octahedron or pentagonal bipyramidal shape. Here in xenon hexafluoride, we get bond pairs are 6 and the lone pairs are 1. Lone pairs are arranged equatorially. And finally, you get pentagonal bipyramidal or distorted octahedron. Now we'll have a look onto the xenon trioxide. What is the shape? Xenon trioxide, sp3 hybridization. Xenon is in +6 oxidation state. Xenon, it is in +6 oxidation state. You get pyramidal shape. Oxidation state is +6 with bond pairs are 3, lone pair is 1. And in the bond pairs, you get 3 sigma bonds and you have pi bonds 3. It is an explosive compound, hygroscopic explosive compound. We'll see xenon dioxydifluoride. Xenon dioxydifluoride, the shape of this one is trigonal bipyramidal or seesaw shape. Dioxydifluoride, you get trigonal bipyramidal, or for this dioxydifluoride, we make it seesaw structure. sp3d is the hybridization. sp3d is the hybridization. And the xenon oxygen is 1 bond, sigma bond, and 2 unpaired electrons present in 5. You get 2 pi bonds with the oxygen. So you get 2 XeO bonds. XeO bonds are 2, that is sigma bonds. And 2 are pi bonds. And 2 are pi bonds with the oxygen atoms. So you get the seesaw shape. Later on, we'll have a look onto the diagrams. Now, xenon oxytetrafluoride. Xenon oxytetrafluoride, the structure, the hybridization is sp3d2. sp3d2 is the hybridization. We are having 5 sigma bonds with 4 fluorine atoms and 1 oxygen atom. The single electron in the d orbital used for the pi bonding with oxygen atom. So sp3d2 is the hybridization. It is having the square pyramidal shape or else octahedral structure. Next, let us see xenon tetroxide. Xenon tetroxide, the structure is tetrahedral shape and the bond angle is 109 degrees. Hybridization is sp3. For tetroxide, you get sp3 hybridization. 4 sigma bonds and 4 pi bonds are there. The oxidation state of xenon is +8. Oxidation state of xenon is +8 with tetrahedral structure. Xenon O3F2 trioxydifluoride. It is having the xenon, it is having trigonal bipyramidal structure. +8 is the oxidation state. Similarly, different compounds can form. Barium, Parzan, xenate, octahedral structure you can get. And xenon oxytetrafluoride, you get square pyramidal. So we have completed the dioxide oxy tetrafluoride. Next, oxydifluoride. Oxydifluoride, you have sp3d2 square pyramidal shape. See. Next, we'll see xenon difluoride. sp3d is the hybridization. Xenon difluoride sp3d is the hybridization. The shape here. This is the section. Difluoride. Now tetrafluoride sp3d2 tetrafluoride difluoride sp3d hybridization. Linear shape. Here you can see linear shape. Geometry is a linear shape. Xenon difluoride sp3d with linear shape. Next, xenon tetrafluoride sp3d2 hybridization. Here sp3d2 hybridization, square planar structure we can observe. The bond distance is 1.95 angstrom. Now the bond pairs you can see and the lone pairs also we can see. Lone pairs are 2 with xenon and bond pairs are 4. Now we'll see xenon hexafluoride sp3d3 hybridization. sp3d3 hybridization. Yeah. You can get for this hexafluoride, we can get pentagonal. Yeah, for this xenon hexafluoride sp3d3 is the hybridization. Pentagonal bipyramidal also you can get, or the octahedral shape. Pentagonal bipyramidal or the octahedral shape we can draw. Now coming to the next one, trioxide. Trioxide sp3 is the hybridization. 109 tetrahedral shape, 109 degrees bond angle, or else you can take even the pyramidal shape. You can even get the pyramidal shape. The bond pairs 3 sigma bonds and 3 pi bonds. 3 sigma bonds and 3 pi bonds. Xenon dioxidifluoride sp3d is the hybridization. Dioxidifluoride, as I've told you the structures. Dioxidifluoride, you're having sp3d hybridization. 5s 3p orbitals and 1 5d orbitals undergo sp3d hybridization. 1s, that is 5s, and 3 5p's and 1 5d orbital undergo sp3d hybridization to form 5 sp3d hybrid orbitals. One sp3d hybrid orbital is occupied by lone pair of electrons. Remaining 4 sp3d orbitals, each containing electron of xenon. Yeah, each containing electron will form 2 of the xenon fluorides and 2 xenon bond oxygen sigma bonds. Here have two xenon fluorides and 2 with xenon oxygens. Xenon oxygen. In these 2 bonds, one is a sigma bond, the other one is pi bond. Here also you are having double bond. One is sigma, one is pi. Next, xenon dioxy tetrafluoride. Dioxy tetrafluoride. We get sp3d2 hybridization. sp3d2 hybridization, where here 5s2, 5p6 and 4d. So one 5s orbital, three 5p orbitals and two 5d orbitals of xenon undergo sp3d2 hybridization. And the five sp3d2 orbitals containing electron, they form five sigma bonds here. And five sigma bonds with fluorine atoms and one oxygen. And the remaining here unused one, this two, they form the pi bonds with oxygen atoms. So it contains a lone pair of the electrons which lies opposite to the oxygen. It has the square pyramidal shape. Then xenon oxy tetrafluoride has the square pyramidal shape. Next, oxytetrafluoride sp3d2. For oxytetrafluoride, we are having dioxy, this is tetrafluoride. Now, xenon oxytetrafluoride, the same sp3d2 hybridization. 1, 2, 3. They form 6 sp3d2 hybrid orbitals. The 5 sp3d2 orbitals containing one electron form 5 sigma bonds with 4 fluorine atoms and one oxygen atom. 1, 2, 3, 4, 5. The single electron in the d orbital, it is used for the pi bond formation of the oxygen. One sp3d2 hybrid orbitals remain unused. So it lies opposite to that of oxygen. So oxytetrafluoride has a square pyramidal or the octahedral structure. Yeah, next, xenon hexaoxide. It is having sp3d2 hybridization. It is having sp3d2 hybridization. Tetrahedral structure, and this is an in the ionic state. So this is the geometrical shape, hybridization, and the oxidation state, and the for this has different compounds of the xenon. So just have a brief look onto today's class. Yeah. Chemistry of the noble classes. Already we have started previous class. And this is the part 2 of the previous class, continuation of the previous class. History we have discussed all the noble classes, how they are inert and how they are considered as a weak bonded species. Now coming to the physical properties also I have discussed the xenon outer electronic configuration, how they are forming the outer electronic configuration, their characteristics. Outer electronic configuration generally it is 0 or 8. So they are called as the zero group elements. And the radius, we can see how it's increasing. Increases from helium to radon. And the ionization potential, it possesses very stable electronic configuration. Ionization potential is very high. So this makes a stable configuration. Next, ionization energy it is very high, decreases from top to bottom. Next, melting boiling points, heat of fusion and heat of vaporization. It's increasing from top to bottom. Yeah, here also you can see the heat of vaporization is increasing from top to bottom. Coming to the melting and boiling points, due to increase in the magnitude of this van der Waals forces, melting boiling point increases from helium to radon. And the solubility, if you see, once if you see solubility, these are slightly soluble in water, increases the solubility increases for the 0 Kelvins from top to bottom. Next, coming to the liquefaction, it is very difficult to liquefy these inert gases because they have weak van der Waals forces of attractions between them. So they have a low critical temperature and thereby it's extremely difficult to liquefy inert gases. The density it is increasing from top to bottom. And noble gases, why inert was also told, it was also discussed due to the stable electronic configuration, high ionization energies, and zero electron affinity. They don't lose or gain the electrons. And due to this energy concentrations, this fluorine and oxygen bond with the 0 group elements and mostly xenon. So xenon compounds we have seen about the fluorides, difluoride preparation properties, tetrafluoride preparation properties, hexafluoride preparation and properties. Next here, difluoride, the properties, tetrafluoride preparations, properties, oxytetrafluoride, same way, the preparation properties. Today's class I started from oxytetrafluorides. And these are the properties, the colorless compounds and the oxytetrafluoride. What is the action of water? What is the action of silica? And xenon oxytetrafluoride, how? Divoxy difluoride. Its preparation and properties for it. Xenon trioxide. Xenon trioxide here I have given you the preparations and properties. Now the structures of the xenon compounds. Structure of the xenon compounds: difluoride, linear shape; tetrafluoride, square planar; hexafluoride, pentagonal bipyramidal; and xenon trioxide is pyramidal shape. Coming to the dioxy difluoride, +6 is the oxidation state, trigonal bipyramidal shape; oxytetrafluoride, square pyramidal shape; tetroxide, it is tetrahedral shape; trioxy difluoride, it is trigonal bipyramidal shape. Here the shapes are written. Difluoride, you can see the shape, linear shape; hexafluoride, sp3d2, you can get the octahedral shape of distorted square planar. Here hexafluoride, sp3d2 d3 hybridization, octahedral shape, or pentagonal bipyramidal you get due to this lone pair of electrons. Trioxide, you are having sp3 hybridization. Dioxy difluoride, sp3d hybridization, a lone pair you are having. Now coming to the dioxy tetrafluoride, sp3d2 hybridization, tetrahedral shape. Next, oxytetrafluoride, sp3d2 hybridization, and xenon hexoxide, it is in the ionic state, sp3d2. Here is the shape. So these are the compounds we have prepared. I have explained you about the xenon compounds, that is halides, oxyhalides, oxides. And in the zero group elements, you still have some of the peculiar compound formation. That is the clathrate compounds we have, the cage compounds, post guest molecule you can otherwise call. How this cage compounds, inert gases or the noble gases such as argon, krypton, xenon, all these form number of compounds. The gases are trapped in the cavities of the crystal structure. They're trapped in the crystal structure for the organic or the inorganic compounds. For example, you can take phenol, hydrophenol. Under different pressures, they get trapped in the cavity, and the inert gases are there enclosed in the crystal lattices of these organic molecules. And these are enclosure compounds called as clathrate compounds. Cage compounds. The substances having cavities is known as the host, and the noble gas which is enclosed in it is called guest. Thus, a clathrate or the organic or inorganic molecule. Thus, the clathrate it is equal to organic or inorganic molecule, host molecule, plus inert gas, guest molecule. So, the guest components in clathrate compounds are held by the van der Waals forces. So, these are all held by the van der Waals forces formed by the host substances. Hence, there is no chemical bonding in these compounds, but the cavities, the host structure gets completely filled with the non-stoichiometric compounds. Quinol argon, quinol krypton, quinol xenon, hydroquinone krypton, kryptonates. All these are the cage compounds. So these zero group elements form different types of compounds. So generally these have very less reactivity, but they form the less reactive in the sense I can tell you due to filled electrons, completely filled electrons in the valence shell and zero valence electrons. They generally don't form compounds, but with oxygen and fluorine, they form. I've told you the energy due to this energy concentrations. We can give the explanation about these compounds. They form oxides, fluorides, oxyfluorides. So oxides, halides, and oxyhalides. This is the end of the topic. I hope everybody have understood about the noble gas, the chemistry of the noble gases. Thank you, everybody.